Hi, I'm Tim, and this is the third in the series of Antigravity Matter videos. This one deals with AGM drag and Bok globules. This video is only an overview. If you want more detail, see the Antigravity Matter document linked to the website. So, we've looked at what happens to antigravity matter around a stationary normal matter object. But what happens when the normal matter object is moving? The antigravity matter gets pushed closer to the leading face of the moving normal matter object, and it gets dragged away from the trailing face. At the leading face, the antigravity matter is closer and denser, so the normal matter object feels a drag force that's mediated by antigravity. The drag force reduces the kinetic energy of the normal matter object, and that energy is transferred to the antigravity matter in the form of turbulence and heat. And here's an example of that. This is the star Mira. Mira is moving quickly through the Milky Way galaxy, and it clearly has a drag tail behind it. So why does Mira have a drag tail when lots of other stars that are moving quickly do not? And the answer is that Mira is a binary system. It's a red giant with a white dwarf, and the probable explanation is that the white dwarf is tearing material off the red giant, flinging it into the space around the system, and some of that matter strays beyond the AGM boundary and gets caught by the antigravity matter wind. It then gets taken backwards and stretched out into a tail behind the star. So this might be a demonstration that antigravity matter and normal matter do interact on a particle level, because that might be the mechanism for antigravity matter dragging on the normal matter that forms the tail. On the other hand, it might be that the normal matter is in sufficiently dense lumps that drag can be applied via antigravity. It's not difficult to find examples of drag tails. Top left is a single star with a drag tail. Top, middle and right are galaxies that have drag tails, so the antigravity matter is passing through the galaxy, between the stars in the galaxy, and it's scouring out the molecular matter and stretching it out in a drag tail. The Magellanic Stream is a tail of molecular matter that actually leads the Magellanic galaxies. What happens to two objects in orbit if one of them is gently slowed is that the slower one falls to a lower orbit, speeds up, and overtakes the one that isn't slowed. So the Magellanic galaxies are orbiting the Milky Way. The molecular clouds within the galaxies are being slowed by the antigravity matter drag. They fall to a lower orbit, they speed up, they overtake the galaxies, and they become a leading tail. And bottom right is a picture of molecular clouds within our galaxy. So let's move on to Bok globules. Bok globules are small molecular clouds that are particularly dense. Here are a few examples of them. Bok globules also often have this globular appearance. So we know that a normal matter object can repel the antigravity matter and create a hole in the atmosphere. So what I've got shown here is that happening, except that the normal matter is actually not quite dense enough to completely exclude the antigravity matter from the volume that it occupies. So what happens in the region of space where the antigravity matter and normal matter are mixed? Well, in the short term, nothing much happens at all, they just mix. But in the longer term, the normal matter is cooled. And there are two mechanisms for cooling. One of them is that if the antigravity matter is cold, the occasional particle level interactions will transfer heat from normal matter to antigravity matter. And the other one is that the normal matter molecules and particles that are in the overlapping region will be the ones that have the most energy. So if there is a gentle antigravity matter wind blowing past, those are the ones that will be likely to be stripped away and removed from the normal matter cloud. The result is that the cloud is cooled. The first mechanism is a little bit more complicated than that because, of course, the antigravity matter might be quite hot well away from the cloud, but the anti-gravity matter that's close to the AGM boundary will have been adiabatically expanded, so it will be very cold. Of course, if the normal matter is also mixed, then the material close to the AGM boundary will also be cold. So which one will cool which one? I suspect that if the anti-gravity matter is slowly moving past the cloud, then the anti-gravity matter will win, and that mechanism will cause the cloud to cool. Either way, the cloud gets cooler and denser and smaller, and it shrinks inside its AGM boundary. At that point, the cooling effects stop, and the cloud becomes stable, just filling its AGM boundary. So this average density, where normal matter just manages to exclude the anti-gravity matter from its volume, is quite important, and we refer to it as the AGM exclusion density. And we need to understand the characteristics of the AGM exclusion density because it might vary between different objects. So what we find is that if you were to plot the anti-gravity matter boundary radius against the AGM exclusion density on a log scale, as the mass of the object varies, you would get a line with a gradient of -1/2. So what do we find in practice? It turns out Bok globules fit on this radius against average density graph with a gradient of about -1/2. So this is evidence for the effect of anti-gravity matter. Now what happens when a Bok globule is moving fast through the anti-gravity matter? Well, that's what's happening here. You can see that on the left the Bok globule has a globular appearance that shows that it is dense enough to exclude the anti-gravity matter from its volume. The surface that we can see is the AGM boundary. But over on the right and in the middle, you can see that some parts of the Bok globule have a more smoky, wispy appearance. The globular surface has gone. This is where the anti-gravity matter is mixing with the normal matter as part of the process of tearing up the Bok globule, shredding it, and mixing it with the anti-gravity matter atmosphere. Where the normal matter is dense enough to exclude the anti-gravity matter from its volume, it takes on this globular, almost liquid-like appearance. And where the normal matter is not dense enough to exclude the anti-gravity matter from its volume, it takes on a smoky appearance. These two states we refer to as AGM excluded and AGM mixed. If we zoom out, we can see that that same Bok globule is the one that's just below right of centre, and there's another Bok globule bottom left, and both these Bok globules have smoky tails which are caused by the anti-gravity matter tearing them apart and mixing them with the anti-gravity matter atmosphere. The Bok globules will be cold still. The smoky tails will be taking on the temperature of the anti-gravity matter atmosphere, so they might be getting quite hot. I'm going to end it there. We've added a few more terms to the terminology list. AGM drag and AGM wind are self-explanatory. The AGM exclusion density is the density of normal matter that will completely exclude anti-gravity matter from its volume. AGM excluded is normal matter that is at or above its AGM exclusion density, and AGM mixed is normal matter that is below its AGM exclusion density and is therefore mixed with anti-gravity matter.